Okay.
Yep, and just while we are all there, I'll just introduce myself again. So I'm David Herring. I'm a technologist with TE Connectivity. And so today, what we'll talk about is a taller OCP NIC, some background, progress, and potential. Okay. We could advance to the next slide. Oh, does everyone want to introduce themselves as well?
Sure, I'm John Lewis. I'm a distinguished engineer at Dell Technologies.
I'm Jonathan Cohn. I'm a Director of Network Adapters in NVIDIA.
I'm Ying Hong, some engineer from Facebook.
Okay. Next slide, please. The first thing to touch on is what is the motivation for a taller OCP NIC? For those that attended the Global Virtual OCP Summit earlier this year, we gave a little teaser out there of some things that could be coming. And a taller SFF was one of those. And the considerations for this could be potential non-NIC use cases, the need to support a 400 gig NIC and the relative pluggable IO, and also to address some increased thermal capability. Next slide. As we first look at what those two different potential use cases are, one was the non-NIC use cases, which is illustrated on the left. We have potential mini-SAS HD external or CDFP style 1, and we look at the heights of those cages and then compare that to the current definition of the small form factor OCP NIC. Then we also have the 400 gig NIC use cases, which the ideal pluggable form factors for that are QSFP double density. We have OSFP writing heatsink version and a typical OSFP. And so now we'll get a chance to, what do these enable? The non-NIC use cases can enable primarily passive copper connectivity, potentially external PCIe cabling, things like that. And then we also have the 400 gig NIC, which is now going to enable other connectivity such as passive copper, active copper, and optical connectivity. We'll go to the next slide. As we first look at non-NIC use cases, what are the height constraints, to adjust the faceplate just to support these IOs? Looking at mini-SAS HD, we are looking at potential height increases of the existing height plus 2.7. And this would, be ideal. It's got a shallow depth behind the faceplate. And then we also look at CDFP, which could enable up to by 16 on a single port. This is also relatively shallow behind the faceplate, but would also be suitable for the existing faceplate height plus 5. And these dimensions we'll actually touch on because they align with some of the 400 gig NIC proposed heights in the following slides. Next slide, please. As we're looking at what are the thermal implications, we need to be prepared for where is this NIC going to be for both cold aisle and hot aisle applications. And what is our ASIC limitation and how can we improve the cooling of that as the power of these ASICs may increase? And then we also need to consider the pluggable medium itself. What is the power going to be for this pluggable IO? What are those options? These options do consider both QSFP double density and OSFP and both variants of OSFP. And qualitatively, just from a module perspective, there's some efficiency differences that are just in the details of the design compared for the thermal resistances, the amount of area available to pull heat out of a module, and then the complexity of the interface itself from a signal integrity standpoint. So there's trade-offs that would need to be considered, which is why these form factors also have interests in this 400 gig application. Okay. Next slide. So now when we look at these 400 gig options, we can see there's 3 different nomenclatures of form factors that are designated here. We have the SFF, which is the small form factor. We have the TSFF, which is the tall small form factor, which is kind of neat. But that also has the plus 2.7 that we saw with MiniSAS HD for the non-NIC use case on the previous slide. And then we also have the ETSFF, which is the extra tall small form factor. And that has that existing height plus 5, which was also shown for the potential CDFP compatibility non-NIC use case as well. The differences and some quick pros and cons, the QSFP double density and OSFP writing heatsink versions, they do offer some thin flexibility, how you're going to couple the module to the cooling strategy for fin height flexibility in the air-cooled environment or other. And then you have the typical OSFP where your module has your heatsink integrated into it and it's at a fixed height. Okay, we'll go to the next slide. And now I'll pass it over to Yin.
Hi, everyone. This is Yin, someone junior from Facebook. For the following couple slides, I would like to talk about the thermal comparison study among the form factors showing in the table here. So I will walk you through the thermal performance of the QSFP-DD, OSFP rising heatsink, and OSFP typical form factor modules applied to both tall small form factor and actual tall small form factor NIC card. The biggest driving factor here to impact the thermal performance is the different heatsink height that can be fit into the NIC form factor. Next slide, please. So we studied the thermal performance for the following 4 modules. So the QSFP-DD in the tall small form factor and the actual tall small form factor. OSFP typical in the actual tall small form factor due to the cage is much higher and not able to fit in the tall small form factor. And also the OSFP rising heatsink in the tall small form factor. Here my assumption is all are from the air is coming from the cold air from the front of the NIC to the back side of the NIC. With different height definition, we are able to design different heatsink height on the top of the cage, except of the OSFP typical, which has integrated heatsink on the top of the cage. The rest of the cases will have the metal to metal contact between the base of the heatsink, base of the cage and top of the cage and the base of the heatsink. So that will be impacted the thermal performance. Next slide, please. This page shows the simulation results for different form factors. In this study, we assume 25 watts NIC ASIC power and 12 watts AOC power. There is 4 plots showing like the different performance for the different form factors. According to the study, we draw the following conclusions. First of all, the tall small form factor QSFP has a similar performance as the actual tall or OSFP typical, which requires about 230 to 240 LFM to cool the 12 watts AOC application under 30 degrees C ambient. Although OSFP has larger heatsink contact area and integrated heatsink design, OSFP cage itself is also taller than the QSFP-DD cage, and therefore it has limited heatsink height that can be put on the top of the cage. Additionally, here the heatsink design itself might also impact the final conclusion. The second conclusion we draw is the actual tall small form factor QSFP-DD cage gets the best thermal performance among the 4 form factors because there are actual room available on the top of the cage that can put the taller heatsink. Under 30 degrees C ambient, it can support up to 12 watts AOC cooling at the typical server airflow range, which I showed the green region in each of the plot here. And the third conclusion will be the tall small form factor OSP rising heatsink has shortest heatsink fin height available on the top of the cage. It can the performance is slightly lower than the rest of the form factors showing here. It can support up to 9 watts AOC cooling under 30 degrees C ambient condition. So there are the thermal performance comparison from my side. And then I will hand over to Jonathan from NVIDIA to talk about their thermal studies.
Thank you, Yin. So I will continue. And I would like just to note that I will talk about both TSFF and ETSFF form factors. And the TSFF form factor is a collaboration work between Dell and NVIDIA. It's a form factor that fits both of our needs. So when John gets to speak about his study, you will see also that the TSFF is good for their needs as well. So our case study that we started with is a 200 gigabit per second OCP3 project, a chip power of around 20 watts, QSFP optical module power of 2.5 watts each, and the airflow direction is hot aisle. As you can see, this is a dual QSFP OCP3 small form factor project, and what I would like to show here is the difference in thermal performance when moving from one height to the other. So in the small form factor, we see here 2 lines in the graphs. It will be the blue one and the green one. Let's for this presentation notice the green one. There is a small form factor with a flat heatsink on the ports, and the TSFF is exact same design, just that we increase the height of the heatsink on both the QSFP port and the ASIC itself, and you can see that the TSFF is better thermally in about 100 LFM at 55 C ambient and about 1.5 degrees. And ETSFF, again, here we increased the height even more. Did not change any of the design, just added height to both heatsinks, did not change heatsink technology or anything like that. And we saw an additional thermal performance increase in again about 100 LFM less than the TSFF, and about 1.5 degrees lower at 55 C ambient. Now, when we look at the OSFP, RHS, and OSF rating heatsink and OSFP, the case study that we chose here is a 400 gigabit per second project on the OCP3. Chip power here, of course, increases since this is 400 gigabit per second. We chose an ASIC of about somewhere between 25 and 30 watts. The OSFP power, we just took a 9 watt OSFP optical module power, which is twice the 200 gig 200 gig optical module, so it's 4.5 times 2. The airflow direction is a hot aisle, and here what we can see is we started with TSFF, since OSFP RHS can fit only in a minimum of TSFF height. So TSFF without heatsink, we can see the blue curve on the left. We have the ETSFF OSFP writing heatsink, which will show similar results in TSFF. Actually, it's the same cage. We showed it in the ETSFF form factor, but we saw same results for the same cage in TSFF form factor. And as we can see here, at 55 C ambient in hot aisle, we can't cool this. It's actually, we can't cool the optical module. That's the weakest link here. There's no issue with the ASIC itself. So when we move to the ETSFF with the OSFP, the regular OSFP with the integrated heatsink, we see far better results, about 10 degrees lower, and we can see that we can converge to about 500 LFM at 55 C ambient, something we cannot get even near when we use the writing heatsink cage. So just a few words about the dimensional changes. So in TSFF, the restricted connector height is 12.83 millimeters. The restricted component height is 14.2, and the faceplate height is 17.8. In the ETSFF, we see an increase of about 2.3 millimeters. So the restricted connector height is 15.13 millimeters. The restricted component height is 16.5, and the faceplate is 20.1. So now I would like to show here how these form factors fit in a 1U rack. So we have here both a picture of the 1U with a combination of PCIe chem card, OCP3, TSFF, and OCP3 SFF and OCP3 ETSFF. So we can see that PCIe chem card can fit only with an OCP3 SFF. TSFF and ETSFF will not fit with the chem card in a 1U rack. When we move to TSFF, then TSFF can fit with either TSFF OCP3 or with the SFF OCP3. And when we look at the ETSFF, then in a 1U rack, ETSFF can fit only with an OCP3 SFF form factor. So if there's a question of why did we not increase the ETSFF even more for even superior thermal performance, then this is the reason why. We didn't want it to take all the space in the 1U rack. We wanted to be able to put another card above it, so it does fit with the SFF card. So just another comparison of all form factors in one chart. So we have the dimensions A, B, C, D, E, which are taken from the OCP spec. These are the only dimensions that were changed when moving to TSFF or ETSFF. All the other dimensions stay the same. So I won't go over all the numbers, but you have it here in the presentation. So it's both, I talked about connector height and component height. We have here also the faceplate height, and they're all in one table, so you can see the comparison between them. And again, these are the only dimensions that we had to change in order to move to those two new form factors. Okay, now I will let John Lewis from Dell to present his slides. Thank you.
Thanks, Jonathan. So we wanted to bring forward an early concept for a a proposed change to the latching mechanism that is in the SFF. And the proposal here is such that we can fit the SFF. It would also work with the TSFF and ETSFF vertically into a 2U, as our diagram here at the bottom shows. And the reason is quite obvious. It allows you to stack these in much more readily. And the latching mechanism allows you serviceability on a card-by-card basis from the outside without the thumb screw or any other mechanism. And of course, the thumb screw is much wider and it wouldn't fit into the 86 millimeter or 84 millimeter envelope. And so the early concept idea, it includes the latch. It is a modification of the latch that was that is currently in the SFF specification. It's been reduced to 76 millimeters so that it is aligned with the faceplate. It does allow vertical insertion and removal in the 2U, and it's externally serviceable. This compares to the other existing faceplates and latching mechanisms, the internal lock, which is not externally serviceable, and the latching mechanism or thumb screw that is not available in the vertical orientation, but is externally serviceable. So it's an effort to try to hit the both yeses in the vertical orientation and the external serviceability. We plan on doing more work on this, and we will be bringing that forward to the OCP NIC MES subgroup for consideration into a future spec revision. Next slide, please, Jonathan. Which brings me to the call for action. We're always looking for more people to join and participate in the sub-project meetings. We have multiple ways to get involved. There's a mechanical subgroup, there's a thermal subgroup, there's an SI subgroup, there's the OC, and then there's the OCP NIC MES sub-project. And we're always glad to have other views and contributions from other companies and people. We have a real interest in how do we specify the non-NIC use case. Let's get that discussion started. What do we need? What can we carry over from the NIC use case so that it's expedited spec writing? And then we have the URLs there. How do you get additional information and how do you get involved? And I think at this time, we have some time for questions and answers.
Hi, team. Great presentation. There's one question. What is the next step on determining which form factor the group will invest in?
Well, I think the next step is discussions in the sub-project meeting. Is there a desire to have both? Is there a desire to only have one? And then, work out, I think, the NVIDIA team has done a tremendous job at working out a lot of the details, along with the thermal work from both NVIDIA and Facebook. We saw David's presentation earlier on the 400 gig use case, and then we need just to make a decision. I think that both are viable. but it's going to come down to the will of the group as to whether we have 3 heights or 2 or stick with the existing one. I believe that the use cases that have been shown warrant the additional heights. The OCP NIC 3.0 has become incredibly popular, and it is expanding daily in the use cases that it can support and the servers and systems that can be supported. And I think that the progress to 400 gig is important.
Another question came through from Jack. How about the compatibility with co-packaged optics?
So,
David?
yeah, I'll give it a shot. I would say, we didn't focus on that specifically in these exercises, but I can imagine that some of the methods that are being considered for packaging co-packaged optics could facilitate a passive fiber from a chip to the faceplate, and having a passive interconnect at the faceplate for external access would fit within that, and leave room for other perforation needed for airflow. And then, should it be needed, there may be even possibilities for some internal interconnect. So I don't think faceplate as size for that it would work within some of the considering heights that are currently being looked at.
So I think that the next question that I see in the chat window is what would be able to be leveraged between the TSFF, ETSF versus the existing SFF definition. And the answer to that is really what has been done is an effort to keep the what I'm going to call the PWA assembly the same. And so you can use the same base assembly, and what you're changing is mechanical components such as the faceplate. The heat sink on the ASIC can grow in height and Z height. And then you have the option of being able to put on heat sinks onto your optics. So you have more Z height, but the other 2 dimensions are the same, and it's expected that the base board and initial assembly is identical. So I believe earlier Kate mentioned that the presentations can be downloaded from the portal.
Yep, so in the FN Virtual portal on this session, if you scroll down on the right-hand side, it'll say additional media links and presentation slide, and a little downloadable link that you can click to download the presentations throughout OCP Tech Week.
Hey, Katie, I see the first presentation from David, but I don't see this presentation in that link, that's all.
You may have to refresh since you're kind of on the back end, but I will take a look at that.
Thank you very much.
All right, we still have a little bit over 10 minutes. Are there any other questions? I have a couple people on the line. If you'd like to unmute yourself, feel free to ask the group some questions, or you can drop them into the chat box in the FN Virtual platform.
maybe since this is an open discussion, we can maybe put something out there for for the audience that has seen the presentations today so far. Are the concerns or the aspects that are being addressed, are they satisfying the needs that you currently see?
Yeah.
Anyone in the audience have some concerns or considerations they'd like to see be addressed?
Yeah, I want to see this. Currently, we are looking into this topic from a 400G angle, and I would like to understand whether this can be extended to the next generation beyond 400G. From a thermal, power, and connectivity perspective.
Yeah. I would say from an I/O form factor perspective and the bandwidth with the next generation signaling transports that are coming, that it would be future proof for next generation. Thermals would definitely be the next question, and maybe some of the trends that brings, and the challenges and some of the limitations on the system side that need to be addressed.
How about from thermal and electrical side?
Well, I think if you look at what's necessary to go beyond 400 gig, it's something other than PCIe Gen 5. So if we assume a Gen 6 implementation, I'm not sure that much, if any, work has been done to prove out the TA1002 connector that we're using at those speeds. Although that's probably something that should be done once the PCI SIG, really gets the signaling stable. So that would be the only way to get more than 400 gig of bandwidth on the small form factor. Of course, the large form factor, you could run 32 lanes and get 800 gig of bandwidth on there. From a thermal perspective, we are fairly limited in the hot aisle over what we can cool in the small form factor today. And both the TSFF and ETSFF provide significant headroom. But if we go back to the NVIDIA slide, as they were hot aisle, you'll see that, given I think it was a 35 watt ASIC, or maybe it was 30, that you still need 500-600 LFM of 55-degree air across it to cool it, and that the optics are the weak link there. That it's going to be very challenging to get above 400 gig in the near future. I think it's going to be possible in the long term, but I don't know about the signal integrity through the connector and what generation of optics modules we might need to wait for in order to get the power down sufficiently that we can cool it.
Yeah, that answers my question.
Great, thanks, Damien.
We have about 5 minutes left. Any other questions or topics you'd like to cover in this open discussion?
Yeah, just to maybe reiterate some of the, call to action to the community, really encourage everyone to come participate and have your voice heard so we can, try to build the most successful ecosystem, that we can. So please come join our groups and participate.
There's a question on the chat. What's the effort being made to minimize the overall number of OCP NIC 3.0 form factors while keeping these new features, the new important features in mind?
Well, I'll take a stab at this since no one jumped right in.
It is a hard one, I say.
I think it's a very hard one, and I think that that actually we're kind of addressing this from a use case perspective on how how our customers, whether it's a card manufacturer and OEM, are using the cards while trying to pack as much as possible into the system. And so, obviously we're going to split up the available market if we have multiple different heights. However, we are using the same base PWA and trying to drive the consistency there. When you look at the use cases for 400 gig and hot aisle, you can see that the QSFP DD is just not going to work. We have to go to something else. And really, for the optics, I believe that the OSFP is the best choice, and that requires the ETSFF. The downside to that is you can't stack two of them in a 1U, as the NVIDIA presentation slide showed. And thus the TSFF allows the very compact stacking in the back. And at Dell for storage, we need that. We need to maximize the I/O at the back of the server. And so that height was chosen specifically so that you could stack two of them in a 1RU height. So I didn't completely answer your question, April, but I gave it a shot. And I think it's
that's great. Thank you.
Okay.